Hello guys. So in this discussion, we'll be doing lecture number 12, Functions as Power Series. So our goal is to find power series representations of some elementary functions. Let's start with the following recall. A series of the form given by this. So sum c sub n times x minus a raised to n running from 0 to plus infinity. And if we expand this is just c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus and so on, where x is a variable and a is a fixed real number, and the cn's are constants. This is called a power series centered at a or power series about a. Okay? Some important note. These constants here, which we will call coefficients, okay? Cn is the coefficient of the term x minus a to the n. So the subscript Cn here, okay, corresponds to the power of the x minus a. So in particular, your c sub 0, this is the constant term, because you don't see the term x minus a here or the factor x minus a here. Its exponent is actually 0. Okay? Here you have c sub 1. It's the coefficient of x minus a. So the power of this is 1. We have the c sub 1. C sub 2 is the coefficient of x minus a squared. So power is 2. Subscript is 2. If you have c sub 2k minus 1, we have the subscript 2k minus 1. So we expect that this is the coefficient of the term x minus a raised to 2k minus 1. And so on and so forth. Okay? Now, two important theorems that we will be using a lot of times for this discussion is the following. First, if you have the power series, this power series here, and if it has a radius of convergence r greater than 0, then the function f defined by this. So f of x equals the power series, okay? This is differentiable and therefore continuous on the open interval a minus r comma a plus r, and the derivative of this function is given by this expression. Okay? The radius of convergence of the power series for this f prime of x is also r. Okay? So in short, if you get the derivative of this power series, all you need to do is to get the derivative of term by term. So if we do that, let us expand this a little. So in here, you have the derivative with respect to x of the constant c sub 0 plus the derivative with respect to x of c1 x minus a plus the derivative with respect to x of c2 x minus a quantity squared plus so on and on. And notice the derivative of the constant is just 0. For this, you'll just get what? C sub 1. So you get here C sub 1 plus. In here, if you get the derivative here, you will get 2C sub 2, then x minus a. Plus, if you continue with this, okay, you will be able to rewrite this as a sum, okay, as a sum as follows. Sum, so notice we now have n starting from 1. So n equals 1 up to plus infinity of we have here. So when n equals 2, you have 2c2 x minus a raised to 1. Okay, if you continue with the third part, you will get 3c3 x minus a raised to 2. So what you will see is the following terms. N, C sub n times x minus a raised to n minus 1. Okay? So for this part. Okay? And then the second theorem is the following. So if you have the power series and it has a radius of convergence r positive, then the function f defined by this power series, okay, is integrable on the interval a minus r comma a plus r. Okay? And also, if we get the integral of f of x dx, we have the following expression. Okay? And also, the radius of convergence of this series here is also r. And just like in the previous theorem, in short, if we want to integrate the power series here, all we need to do is to integrate term by term. Okay? So if we do the computation, we can expand this. The expansion is this guy here. Okay, the expansion is this guy here, and you will get this expression here. Okay, so notice if you do the differentiation from n equals 0, it started now and at n equals 1. For the integration, n equals 0 is still the starting point. Okay, so we will use these two theorems, okay, and some known power series in order to write other power series or other functions into their power series representation. Okay, so let's start with this first example. We want to find the power series representation for this function, and then we want to give the interval in which this representation is valid. So in order to do this, first let us recall the following power series. Okay, and we will use this. So we know that if the absolute value of x is less than 1, then we can look at here the series x to the n and from 0 to plus infinity. And we know this is just a geometric series, and since the absolute value of x is less than 1, we know that this is equal to 1 over 1 minus x. So how is this useful? We look at this, okay? We will try to convert this into the following expression with some modified x here if it is coming from here, okay? So what I'm saying is, from this function, if we factor out 4, okay, and the denominator, then this function here can be converted into 1 over 4 times 1 over 1 minus x over 4. Okay? And therefore, if if the absolute value of x over 4 is less than 1, then we can use this representation, okay, to get 1 over 4 minus x equals 1/4 sum from n equals 0 to plus infinity of x over 4 raised to n. And if we simplify this, we will get sum, or let's put the 1/4 first, okay, 1/4 x to the n over 4 to the n from 0 to plus infinity. And since here 4 is independent of n, we can put it inside the series so that this 1 over 4 minus x can be written as sum from n equals 0 to plus infinity of x to the n over 4 raised to n plus 1. And take note, we have this assumption. Absolute value of x over 4 is less than 1. So this power series representation is valid in this interval. Okay? So if x is within -4 to 4, okay, then we have 1 over 4 minus x. This is the sum x to the n over 4 to the n plus 1, and from 0 to plus infinity. Okay? For our next example here, find the power series representation for the function below and then give the interval in which it is valid. So notice our f of x is equal to x over 4 minus x quantity squared. And there's a denominator 4 minus x. Its power now is squared. So maybe we can use this representation. Okay? In fact, we will use this representation here to get a power series representation for this expression. Okay? So from the previous example, we have the following. From the previous example, if absolute value of x is less than 4, then we have 1 over 1 or 4 minus x. This is equal to the series x to the n over 4 raised to x or 4 raised to n plus 1, and from 0 to plus infinity. Okay? So what we're going to do to obtain 1 over 4 minus x squared, you just need to get the derivative of this. Okay? It follows that we get the derivative with respect to x of 1 over 4 minus x. So this is equal to the derivative with respect to x of the series x to the n over 4 raised to n plus 1, and from 0 to plus infinity. And for this guy here, we shall get 1 over 4 minus x quantity squared. Okay? Whereas for this guy here, using the theorem, we will have the sum from n equals 1 up to plus infinity. So in here we have n, x to the n minus 1, divided by 4 raised to n plus 1. Okay? And therefore, if we want this, we'll just have to multiply this by x, and let's just multiply this by x. So therefore, f of x, this is x over 4 minus x quantity squared, and this is equal to x times the series n x raised to n minus 1 over 4 raised to n minus 1 or n plus 1, and from 1 up to plus infinity, and this is just the sum n from 1 up to plus infinity of n times x raised to n over 4 raised to n plus 1. But take note that since this series here is valid only in this interval, we have to put that condition. So let's just write it here. Therefore, if absolute value of x is less than 1, okay, then our f of x which is given by this, will be this guy here. Okay? So this is the power series representation of this function. For our next example, find the power series representation for the function below and give the interval in which the representation is valid. So this time we have f of x equals 4 over 8 plus x cubed. So we'll just use the same. We'll just use the same initial series. So that's this series here. So that's this series here, right? So what we're going to do is to factor out. So for this, we just need to factor out the 8 in the denominator. So in here, we can rewrite this as 1 over 8 times 4 over 1 plus x cubed over 8. Okay? And then we'll just simplify this. And then here, let's try to rewrite this as a single expression. Take note that, or as a single power, take note that 8 it's just 2 cubed. So you can combine this into a single rational expression and then you cube it. Okay? So anyway, you have 4 over 8. That's 1/2 now. And then you have times 1 over 1 plus x over 2 quantity cube. Okay? Furthermore, we can rewrite this as 1/2 times 1 over 1 minus, and then minus quantity x over 2 cube. Okay? So let me just put this in square brackets. Therefore, so, okay, if the absolute value, if the absolute value of x over 2, okay, if the absolute value of x over 2 raised to 3 is less than 1, okay, then we have 4 over 8 plus x cubed. This is equal to 1/2 sum of negative quantity x over 2 raised to n, okay, and running from 0 to plus infinity. Oops, sorry, I forgot the 3 in here, okay. But anyway, so if we simplify this, we will have 1/2 sum n from 0 to plus infinity. You will get negative 1 raised to n. And then you will get x raised to 3n over 2 raised to 3n. And then if we bring this 1/2 inside this power series, we will get the series from n equals 0 to plus infinity, negative 1 raised to n, x raised to 3n over 2 raised to 3n plus 1. Okay? So again, this one is valid only in this interval. Okay? But notice if the absolute value of x over 2 cube is less than 1, if you take the cube root of both sides, the inequality remains the same. Okay? So this guy here is valid. Okay? So the series, the power series representation is valid. um, on the interval -2 to +2. Okay? So again, it can be obtained using this guy here. So anyway, let's just write the detail there. Okay? So you will have the absolute value of x over 2 less than 1. You take the cube roots of both sides. Um, since they're all positive anyway, uh, the inequality will remain um, less than. Okay? And this will give us what? The absolute value of x less than 2. That's why we have this interval here. Okay? For our next problem. So this time we want the representation for f of x equals ln of 3 plus x. Okay? So now, how are we going to do this? So again, if absolute value of x is less than 1, then we have 1 over 1 minus x equals the series x to the n, and running from 1 or from 0 to plus infinity. So what we're going to do is to integrate this. So if we integrate this, integrate 1 over 1 minus x dx, all we need to do is to integrate also this. So integral of the series x to the n and from 0 to plus infinity dx. So if we do the integration, we will have negative ln absolute value of 1 minus x. And then on the, of course, there's a plus c in here. There's a plus c in here. But we'll just put the plus c on the other side. So for this guy here, we just have the series from n equals 0 to plus infinity of x to the n plus 1 divided by n plus 1, and then there's a constant c. Okay? And then we can find the value of c in here. Okay? So notice when what? Um, when x equals 0, okay, and since 0 is within this interval here, when x equals 0, you'll just have ln or negative ln absolute value of 1. And notice that when x equals 0, all of these are 0. Take note that this does not have any constant term. Okay? So on the right hand side, you'll just have c. But this implies your c equals 0. So basically, you have ln absolute value of 1 minus x. This is equal to negative sum x to the n plus 1 over n plus 1, and from 0 to plus infinity. So now we will use this, okay? We will use this to solve or to find for the power series representation of this function. First, we have ln of 3 plus x. What we're going to do is to factor the 3. So we will have ln of 3 times 1 plus x over 3. Okay? Or this is just what? Ln of 1 plus x over 3 plus ln of 3. So we look at this. Okay? We look at this. So it's just this guy. Take note, since your absolute value of x is less than 1, 1 minus x will always be positive. So basically, this absolute value symbol here, it can be replaced by just the parenthesis. Okay? So if we have the absolute value of x over 3 less than 1, then this guy here, we can now replace it with this expression, okay? But keep in mind, this is plus, this is minus, okay? So let us just write that. We have ln of 1 plus x over 3 plus ln of 3. This is equal to ln of 1 minus negative x over 3, okay, plus ln of 3. Now we apply the power series representation. We have negative of the sum from n equals 0 up to plus infinity of negative x over 3 raised to n plus 1 times 1 over n plus 1. Okay? And then let us simplify this. You have negative sum, and from 0 to plus infinity, you have negative 1 raised to n plus 1. And then you will have x raised to n plus 1 divided by 3 raised to n plus 1 times n plus 1. But don't forget this plus ln of 3 here. So plus ln of 3 plus ln of 3. Okay? And we can bring this negative here inside. Okay? So if you bring that one, or maybe you can take out the negative here and multiply to the negative here. So whatever you do, what you will get is the following. So series from n equals 0 to plus infinity of negative 1 raised to n. X raised to n plus 1 over 3 to the n plus 1 times n plus 1 here, and then plus the ln of 3. Okay? For our next example, now we have the power series representation. We want to find the power series representation of f of x equals ln of 3 minus x squared. So if we recall, you have ln 1 minus x. So if absolute value of x is less than 1, then this guy here is equal to negative sum of x raised to n plus 1 over n plus 1, and from 0 to plus infinity. So for this function, okay, we just rewrite this as ln. Then you factor out 3. So we'll get 3 times 1 minus x squared over 3. Okay? X squared over 3. Or simply, this is just ln of 1 minus x squared over 3 plus ln of 3. So now, to apply this, we need this guy here to be less than or less than 1 in absolute values. If the absolute value of x squared over 3 is less than 1, okay? If the absolute value of x squared over 3 is less than 1, then we have here ln of 3 minus x squared. This is equal to ln of 1 minus x squared over 3 plus ln of 3. This is equal to negative sum from n equals 0 to plus infinity of x squared over 3 raised to n plus 1 times 1 over n plus 1. Then on the outside, you have ln of 3. Okay? Or this guy here, if we simplify, we have negative sum n from 0 to plus infinity of x raised to 2n plus 2 all over 3 raised to n plus 1 times n plus 1 plus ln of 3. Okay? So if you solve this, okay, if you solve this inequality, okay, this guy here, let's just write it here, this is valid on the interval negative square root of 3 comma square root of 3. Okay, so try to solve this inequality and you will get this interval. Okay, for this example we again use the following. So if absolute value of x is less than 1, then we have the series x to the n from 0 to plus infinity, this is 1 over 1 minus x. So for this, we'll just need to write the minus part here so that this guy here can be written as x over 1 minus negative 4x squared. Okay? So, if the absolute value of negative 4x squared, this is less than 1, then x over 1 plus 4x squared, this is equal to x times the series n from 0 to plus infinity, okay, of negative 4x squared raised to n. Okay, if we simplify this, you have x sum n from 0 to plus infinity, you have negative 1 to the n, and then you have 4 to the n, x raised to 2n. And then if we bring this x inside the sum, we will have the sum from n equals 0 up to plus infinity of negative 1 to the n, 4 to the n, x raised to 2n plus 1. So again, this power series is valid on this interval here, okay? But if you calculate this, I mean valid when this inequality is true. If you calculate this and write the interval, you would get this is valid, okay? This is valid for x inside the interval 1/2 or negative 1/2 comma 1/2. Okay. For our next example here, now use the integrability of the power series to express the sum, okay, in the form of an elementary function within the radius of convergence of s of x. So in the previous examples, we have elementary functions and then we convert it to power series. So we reverse now the process. We have a power series. Let's try to find the elementary function that is represented by this inside, of course, the radius of convergence. Okay. First, let's try to find the radius of convergence in here. So to find the radius of convergence, to find the radius of convergence, okay, we try to use ratio tests. Okay, these are all the terms. Okay, so we need to find the limit absolute value of a sub n plus 1 over a sub n as n approaches plus infinity here. But let us formalize this. To find the radius of convergence, we let a sub n to be equal to n x raised to 2n minus 1. Then we have this. So this is equal to the limit as n approaches plus infinity of the absolute value. So you have n plus 1 x raised to 2n plus 1 minus 1 all over n x raised to 2n minus 1. Okay? So if we look at this, we have the limit as n approaches plus infinity of the absolute value. You have n plus 1 over n. And then for this, if you expand this becomes x raised to 2n plus 2 minus 1. So we try to rewrite that as x raised to 2n minus 1 times x squared over x raised to 2n minus 1. So we easily see that this guy here will cancel each other. Okay? And therefore, this is just x squared. So I can now remove the absolute value because x squared is always positive. And then you will have the limit as n approaches plus infinity of n plus 1 over n. And the limit is just 1. So this is equal to x squared. And we want this to be less than 1. Okay? So in here, we need our x. Okay? We need our x to be such that x squared less than 1. But this means we can have absolute value of x less than 1. Okay? You can solve this. What you will get is that, okay, or you will have your x greater than negative 1 but less than 1. So you will have this guy here. Okay? So for absolute value of x less than 1, we were given a hint, integrability of the power series. Okay, integrability of the power series. So for absolute value of x less than 1, we integrate s of x dx. So we'll just have to integrate here the series n x raised to 2n minus 1 dx. Okay? And from 1 up to plus infinity. So if we do the integration on the right-hand side, we'll just get the sum. And from 1 up to plus infinity, remember when you integrate, you don't change the lowest number for n. But in here, you will get n x raised to 2n over 2n. Okay, so 2n minus 1 plus 1, that's just 2n. And therefore, this is just the sum. Okay, I forgot the plus c in here. Okay, let's put the plus c in here. But anyway, you'll just have the series from 1 up to plus infinity of x raised to 2n over 2. And then you have the plus c. Okay? So now we have the integral of s of x dx. Okay? And it's given by this power series. But what is this power series? What is this power series? Take note that this power series here, okay, can be written as 1/2 sum x squared quantity to the n. and from 1 to plus infinity. Okay? And then you have the plus c in here. Okay? But this guy here, we can write it now as 1/2. 1/2 of 1 over 1 minus x squared. Okay? But for this, take note that this has n equals 0 term. So we have to subtract that n equals 0 term. Okay? So quantity minus 1. And then you have the plus c in here. Okay? So how is that? Again, let us look at this power series. So initially, you have the power series 1 over, so you have this guy here, 1 over 1 minus x squared. So this is the series from n equals 0 to plus infinity of x squared. But this one is n equals 0. So when n equals 0, you just have 1. Okay, quantity to the n, sorry. Now, when n equals 0, you just have the constant 1, and then you have the plus series from 1 up to plus infinity of x squared raised to n. Okay, so we have to subtract that 1 from this to obtain this part here. Okay, but now we want s of x. We don't want the integral of x dx. We want s of x. So what we're going to do to bring back s of x is to differentiate this. We will get the derivative of this, and therefore we also get the derivative of this. Okay? So this is what we have so far. If absolute value of x is less than 1, the integral of s of x dx, this is equal to 1/2 times 1 over 1 minus x squared minus 1/2 plus c. Okay? Differentiating, we have, so you get the derivative of this. You also need to get the derivative of this. We now have s of x. This is the derivative with respect to x of this guy, 1/2 times 1 over 1 minus x squared. And of course, the derivative of 1/2 plus constant, they are just 0. So let's just look at this. But this is what? So you have 1/2 times 1 over 1 minus x squared times the 2x. Or simply, this is just x over 1 minus x squared. So this is this sum here. Okay? So practice on the derivatives if you think we have this to get this. Okay? So you can write this as 1 minus x squared raised to negative 1. So if you get the derivative, you have negative 1 over 1 minus x squared, and then the derivative of the denominator, it's negative 2x. So the negatives cancel each other. So you have this. Okay? Finally, okay, within its radius of convergence, express the sum s of x in the form of an elementary function x. So how do we do this? So we can start by looking at s of x in here. Okay, so let's find the radius of convergence first. Okay, let a sub n be equal to x raised to 2n plus 1 over 8 to the n. Then we want to find the limit as n approaches plus infinity of a sub n plus 1 over a sub n. And then this is just the limit as n approaches plus infinity of absolute value x raised to 2 times n plus 1 plus 1 over 8 raised to n plus 1 times. You have 8 raised to n over x raised to 2n plus 1. Then we close the absolute value. So if we simplify this, we have the limit as n approaches plus infinity of the absolute value of x squared over 8. Okay? So you'll get this guy here. Okay? So 8 to the n will cancel the 8 to the n in here. And then here, if you expand this, you will have 2n plus 2 plus 1. So you can separate the 2n plus 1 and the 2. That's why you will end up with this. But this is just constant. This is just constant. So we're good at this. Okay? So this is simply x squared over 8, and we want this to be less than 1. So work on this inequality, and you should be able to show that our x will be greater than 2 or negative 2 square root of 2 and less than 2 square root of 2. So now from here, assuming that our x is in between these two numbers here, let's look at our s of x. So our s of x, this is equal to the sum from n equals 0 to plus infinity of x raised to 2n plus 1 over 8 to the n. What we're going to do is to separate this x to the 1. Okay, so this will be the sum from n equals 0 to plus infinity of x. And then we will write x to the 2n as x squared raised to n. And then on the denominator, of course, we have 8 to the n. And then we rewrite this. We combine x squared and 8 as one fraction and then raise it to power n. Then we bring out our x of the summation symbol. So we will have x sum of x squared over 8 quantity to the n equals 0 to plus infinity. And this guy here, it's familiar to us. And this will be x equals 1 over 1 minus x squared over 8. Okay? So if we simplify this, our s of x will be 8x divided by 8 minus x squared. So again, this is our s of x, okay? Provided that our x is between negative 2 square root of x and positive 2, sorry, negative 2 square root of 2 and positive 2 square root of 2. Okay? So let's just put that for x in between negative 2 square root of 2 comma 2 square root of 2. Okay? So this is my last example. Thank you for staying. I hope you learned some techniques during this discussion. Thank you. Bye-bye.